think that the chiral can be the word of the day. But yeah, I would like to give you some theoretical view on the parity violation and laser-coolable molecules. So for in a very specific, I don't have a pointer. Okay, sorry. Okay, but why ultra-cold molecules? Because why they are why ultra-cold molecules are ultra-cool? Because they are highly controllable. For example, we can trap them. We can perform precision measurements, which is the most interesting part of me. We can put ultra-cold molecule in an optical lattice to study different quantum magnetic systems. We can study ultra-cold chemistry. We can study chemical reaction on very fundamental level. But yeah, precision measurements. So in general, there is a problem with asymmetry. Asymmetry in the universe, because as it was mentioned by the Augustine, there is no answer for the matter-antimatter imbalance. So yeah, CP violating phenomena, CP violating multiple moments with molecules can be help for that. We still don't know why there is asymmetry in the biologically relevant molecules. So we have domination of only one enantiomer of chiral molecule. We can study variation of fundamental constants with ultra-cold systems. But yeah, laser cooling, how it works. So let us assume for a moment that our polyatomic molecule is a two-level system, because why not? So the idea is to have the molecule, our particle, absorb photon, and then there is the excitation. Okay, it doesn't work. The excitation to the initial state. So the issue is to have directional absorption and isotropic emission. In that way, we can create dissipative force and effectively slow down molecules. Well, this is quite nice to have great sensitivity of measurement, different kind of measurements. Okay, but how to design laser-coolable molecule? What kind of molecule can be laser-cooled? So let's look at the very simple diatomic system like calcium oxide. This molecule is not laser-coolable. Both valence electrons of calcium are involved in the bond formation with oxygen. So we see that the geometry of the excited state is quite different from the ground state. So this leads to the vibrational rotational branching, and we can in this case we cannot create closed cyclic transitions, so we cannot create this dissipative force to cool down molecules. But in case of calcium fluoride, there's only one electron participating in the bond. The second electron is unpaired electron. We call this electron optically active electron, and this electron is excited, and then there's emission to the ground state, and in that way, in calcium fluoride, we can cool this molecule down effectively. So there's the next question: can we cool down larger system like 3 atomic molecules, atoms, or even molecules with multiple rings? The answer is yes. It was already done for calcium methoxide. The molecule was cooled down to the 700 millikelvin by a group of John Doyle. So from the definition, this molecule is the symmetric top. From the definition of the chiral molecule is asymmetric top. So maybe there's the next question: can we create chiral molecule that looks like symmetric top? So the idea is, can we, instead of putting only 3 hydrogens here, protium, 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 can we change one protium for the deuterium and the second protium for the tritium? So in that case, we have isotopically chiral molecule. Yeah, we know what the chiral molecule is. This is an example of the amino acid that is chiral. We have asymmetric carbon atom. But for this kind of molecule, for sure, is not laser coolable. So okay, it is super important. The chirality, the problem of this of the chirality is super important. For example, in pharmacy, it was turned out that the 1960s with thalidomide. One enantiomer of thalidomide was in fact a drug. The second one was an extremely toxic molecule. And the result of this toxicity you can see on this picture of the kids with the foam legs and hands. But why is that? It's not because of the internal nature of molecule. It's the reason is because they differently interact with the environment. It's not the internal nature, this toxicity of the thalidomide enantiomer. And as it was mentioned, we have several different types of forces in the nature. Important one for the parity violation is the weak force, because the weak force violates parity. And in fact, exchanging the bosons W and Z between electrons and nuclei can lead to the small energy shift in these chiral systems. And okay, so we have symmetric top molecule like ytterbium methoxide. So let's try what can we do with ytterbium methoxide by the chiral one with isotopically substituted hydrogens. So okay, we can see that the ground state and excited state to some extent have similar geometry. It's a good sign for laser cooling. We can say, okay, there's a chance that this molecule is laser coolable. We can see that this excitation is localized almost only on the ytterbium atom. This is nice for us, for the laser cooling. And to get some numbers describing effectiveness of this laser cooling, we calculated Frank-Condon factors for this system. And you can see on the left-hand side, we have Frank-Condon factors for the ytterbium, non-chiral ytterbium molecule. On the right-hand side, we have the chiral one. The perfect situation is to have these numbers quite close to 1. Of course, it's not the case here, but still, with some repumping lasers, we can get nice laser cooling for these systems. And okay, how about parity violation? So if you are clever enough, then you can take pen and paper and derive from the standard model Lagrangian this effective Hamiltonian and calculate parity violation energy along the normal modes of a given molecule. Then you can calculate electronic energy, and using, for example, Numerov method, you can calculate vibrational shift in this for a given normal mode. As you can see, these shifts here are much smaller than in the case of Yuval's molecule, because it's like 45, 14, 46 millihertz, so they're quite small, but still, this molecule can be laser cooled, so the sensitivity can be greatly enhanced. And this is the hope for us. Yeah, this is what I said. We use the Dirac-Coulomb Hamiltonian. We apply for component DFT with this functional, which is reoptimized for this particular purpose, for the parity violating shift, to get good accuracy of these energies. And yeah, there is a chance to cool down chiral molecule. If the molecule will be cold enough, then even with the small shifts, we can measure it, hopefully. And the issue is also that, to some extent, the requirements for laser cooling and for the large PV shifts are opposed to each other, because for the large parity violation shift, we need large changes in the density around the heavy nucleus. In fact, for the laser cooling, we want to keep this metal atom quite separated from the rest of molecules, to have diagonal Frank-Condon factors and etc. But maybe with a different bonding motifs, for example, using sulfur instead of oxygen, then this molecule is bent, so we can the changes in the density around the heavy metal atom can be larger. So maybe there will be a hope to cool down molecule and have larger PV shifts. So yeah, thank you. If you have any questions, then feel free to ask.
Thank you. Yes, questions.
So thank you for the great talk. So I have a question. So really, you discussed mostly the vibrational Frank-Condon factors.
Yes.
But there are other effects that are used in laser cooling, for example, that involve the symmetry. For example, you use rotational selection rules in order to limit the rotational space in some of these diatomic, and also these apply to symmetric tops. So I wonder if you've taken into account how much these selection rules apply or don't apply, or like are they partially selective, and how
In
bad
principle,
it would get with a chiral molecule.
okay, in principle, the work, I think the John Doyle, they studied this rotational branching also for this asymmetric top molecule, and when we have the molecule that looks like almost like symmetric one, so then we can almost use the selection rules for the rotational transitions to remove this rotational branching. So it's not the perfect situation, of course, because it's still a symmetric top, but yet we can apply this procedure from the symmetric top to these systems and to some extent limit the rotational branching. Of course, there's also issue with this with the vibronic effects like Renner-Teller, Jahn-Teller, etc. But that's a different story. But yeah, it also should be taken into account in the analysis of the laser coolability.
Thank you. There.
So you said one problem is that you want to have large changes around your chiral center in the electron distribution, and that was opposing the laser coolable condition.
Yeah.
So could this be resolved by having the chiral center not directly attached to the calcium atom, but like, let's say, a bit further away?
Once again,
So what if you don't directly attach the chiral center, if you put it further away from the calcium atom, basically? Would this make this condition less?
I mean, no, the issue is to have large changes around this heavy metal atom, so around this green one. So maybe you can remove this oxygen, the red one, to keep the heavy metal atom close to the asymmetric carbon atom. But there's a question: is this kind of molecule without oxygen still laser coolable? It's not so obvious. But for example, when you for example use instead of oxygen sulfur, then the ground state of such molecules is bent. I mean, the angle is not 180; they are bent. So in that way, you can somehow create larger changes in this electron density on near the heavy nucleus. So maybe that will be the possibility.
Are there any questions? Okay, so let's thank the speaker.